All right, welcome to video 2 for the torque unit notes. All right, in this video we're going to actually talk about torque. Torque is rotational force. If you think about, if you got like a lid on a pickle jar, you have to twist that lid off. And sometimes that's hard. That means it takes a lot of torque to rotate that lid to get it free. And if you think about it, it's also kind of like a force. So torque is like a spinning force. If you are a force needed to spin something. So, if we take a look at our linear quantities, we have x. So the rotational equivalent of x is theta. We have linear velocity, and its rotational equivalent is omega. We have rotational velocity or angular velocity. We have linear acceleration, and its rotational equivalent is angular acceleration. We have linear mass, and its rotational equivalent is moment of inertia. And now when we have linear force, its rotational equivalent is torque. So we're starting to make this list here of linear quantities with their rotational equivalents. And what makes this really nice is that means the math is all identical. So for Newton's second law, for translational motion, the net force equaled mass times acceleration. Okay, well, if I look at the net torque, well, what's the rotational equivalent of mass? Oh, that's moment of inertia. What is the rotational equivalent of acceleration? Oh, that's alpha. So here we go. We have Newton's second law for rotational bodies, or rotating bodies. The net torque equals the moment of inertia times angular acceleration. So this is a really, really neat concept if you think about it, because this really helps us out because we've already seen all of this math before. The math is going to be identical. We just have to start speaking in terms of Greek instead of English. All right, so let's think about this. What torque then is needed to accelerate a bicycle wheel? And I want to go with the spoked rim variety. Okay, well, torque, I should go with the net torque, equals moment of inertia times angular acceleration. Well, for a spoked rim, that's the same thing as a hoop. Its moment of inertia is 1/2 mr squared times alpha. So there we have it. Using this formula right here, I would need to know the mass of the rim, its radius, and what acceleration I would like it to have. And if I have those three things, I can then tell you how much torque would be needed to accomplish that. All right, let's revisit the modified Atwood's machine. Excuse me. When we looked at the Atwood's machine before, we said that we had an ideal pulley. An ideal pulley has no mass and no friction. Okay, well now, let's look at a real pulley. A real pulley does have mass, and it does have a radius. And I'm going to say everything in this direction is positive. I'm going to say everything in this direction is positive. And remember, if something rotates clockwise, it's negative, and if it rotates counterclockwise, it's positive. So we have to keep in mind the rotational aspect as well. Now, a pulley is a solid disc. So since this is a solid disc, its moment of inertia will be 1/2 mr squared. I'm going to put a little tiny p beside that mass because it's the mass of the pulley. Also, don't forget we have our bridge between linear and rotational. So the linear acceleration would equal r times the angular acceleration. So let's go ahead and let's tackle this. We're going to start the same exact way by looking at a free body diagram for each. So for block 1, if I were to take a look at block 1's free body diagram, I would have a normal force, I would have tension force, it would have some weight, and I'm going to say there's some kinetic friction. If I were to look at, this is object 1, if I were to look at object 2, the free body diagram for object 2, I would have some tension force, and I would have a weight. Here's where we have to be careful. Since this is a real pulley, that means that the tension on either side of it will be different. When we looked at an ideal pulley, the tension force was something that was the same on both sides. This time it's different, and that's the key. These have different tensions on either side of the pulley. Okay, now going on, when we take a look at the sum of forces on the y-axis for object 1, we have the normal force minus the weight. That equals 0, so that basically tells us that the normal force equals m1g. When I take a look at the sum of forces on the x-axis, I have Ft1 minus the kinetic friction, and this equals m1a, positive because it's going to slide in the positive direction. Now, friction is mu times normal force. The normal force is m1g, so this tells me that I have this expression here. This is equation 1, and I have two unknowns in it, Ft1 and A. Okay, for object 2, it just has forces along the y-axis. So it's at Ft2 minus Fg2 equals negative m2a, because object 2 is going to go in the negative direction. And that leaves me with this expression here. Now, in the past, we solved both of these for tension force and set them equal to each other and then calculated the acceleration. But we can't do that this time because the tension is different. So we need to figure this out. Well, in comes the pulley. On the pulley, the sum of all torques should equal moment of inertia times angular acceleration. So we need to think about what those torques are. Okay, well, if you think about it, there's a force pulling on either side of this. And we're going to learn later on that torque can also be found by taking a force multiplied by a lever arm distance. So what I have here is I've got Ft1, and its lever arm distance is the radius. And notice how it's trying to rotate it in the positive direction. Ft2, it's trying to rotate it in the negative direction. So that takes care of that. And this should equal I times alpha. Now, I need to have a negative sign in front of the I. And the reason for that is because ultimately, object 2 is going to pull down and slide object 1 across the table. So this pulley will start rotating clockwise. So I need to have this negative in front of the I, alpha. Okay, now we can start plugging things in. Ft1, well, I can get that here. I just have to take the mu k m1g and add it over. That's my R. My Ft2, well, I got that right here. I just have to take this m2g and add it over. equals, okay, now my moment of inertia is 1/2 times the mass of the pulley times r squared. And notice that alpha equals linear acceleration divided by radius. So hopefully you can see how I plugged everything into this equation right here. And also notice that we get some algebra. This radius cancels out one of this because that was r squared. And then here, if you think about it, every single r is now gone. So here's what I have left. That's what I have left. And I just have to solve this then for the acceleration, a. So let's get all the a's on the same side. And everything else on the other side. All right, and then the algebra becomes very simple at this point. Keep forgetting my board's messed up at that one location. Okay, there we go. And there we have it. Notice that this looks very, very similar to the formulas that we derived earlier in the year, except that now we have that one extra term right there for the pulley. Okay, so notice that there was a force acting on the pulley and that this force was perpendicular to the radius of the pulley. This gives us a second way to find torque. This is our second equation to find torque. It is a perpendicular force times a lever arm distance. So here's a picture here. We have a lever arm and we have this force. Notice that forces that are parallel do not help to rotate the arm. It is only forces that are perpendicular to the lever arm that will help to rotate it. So we have to make sure we use a little bit of trig to get the perpendicular version. So in this case right here, this torque would equal a force times, if I were to move this over here, this is that force perpendicular. Notice that it's opposite here, so that'd be sine of theta times our lever arm distance. And notice that this will be trying to rotate it in a counterclockwise direction, so it will be a positive torque. All right, that concludes video 2. We have one more video for this unit.